Good morning, good afternoon, good evening, wherever you might be. This post is on the signs of our times. One morning I woke up to see the front page of every newspaper across the world covered with pictures of what looked like a big orange donut. What could this represent? I learned that the donut picture was rendered by combining images taken from telescopes all over the world. Petabytes of data had been mailed to one location for analysis, and a few groups of PhD students wrote some code to combine and overlay the images. The student responsible for combining all of the work into one image got something that looked like a black hole, and newspapers and magazines from around the world put that picture on the front page. Each individual image in the data set showed no hole, just a blur. When I saw this, I thought, well, PhD student work is nice to have, but it often contains mistakes. So I sure hope her advisor went through her code very carefully, because if you overlay petabytes of images with individually tuned contrast ratios and construct your algorithm so that the overlay is centered around a region of interest, it is certainly possible to create a black hole in the region of interest. You'd think this sort of scrutiny is routinely applied to new results, but in the darkened conference rooms in which data is presented, skepticism is expressed in hushed and veiled terms. Sometimes nothing stands in the way of an idea marching ahead. So, the first article I read had a bit of detail on how the algorithm was developed that created this image of a black hole that appeared on the front page of all of the newspapers. Miss Katie Bowman adopted a clever algebraic solution to this problem. If the measurements from 3 telescopes are multiplied, the extra delays caused by atmospheric noise cancel each other out. This does mean that each new measurement requires data from 3 telescopes, not just 2, but the increase in precision makes up for the loss of information. Okay, fair enough. But it's really not enough to make an assessment of how sensible the data analysis was. I wanted to see her present her data, but what I found was a TED Talk, which is not the same thing as an academic presentation. The thing that concerned me most from the TED Talk was when she said, at 6 minutes in, I paraphrase, "Some images are less likely than others, and it is my job to design an algorithm that gives more weight to the images which are more likely." Wait, my understanding of the scientific method is raising red flags at this statement. She told her algorithm to look for pictures that look like black holes, and lo and behold, her algorithm found black holes by ignoring data that didn't look like black holes? This doesn't sound like the scientific method I remember. But then again, the Gravitational Wave Observatory, LIGO, did something very similar in their algorithms. So if they got away with it, why can't she? Finally, I found a real academic presentation from shortly after the media blitz and front page news stories. It is an hour long, and the technical material starts about 10 minutes in. I'm going to go through some of it. At 14 minutes in, she talks about the challenge of dealing with data that had an error of 100%. What? If your data has an error of 100%, isn't that just noise? I'm confused. At 16 minutes in, she talks about how her clean algorithm, clean is an acronym for something, it's guided a lot by the user, as in the user makes the image look how they think it should look. This is also not sounding very good. At 19 minutes in, she said, most people use this method to do calibration before imaging, but we set it up so that we could do calibration during imaging. Oh, dear. So they calibrated each image to look how they thought it should look, and they had petabytes of images. Ugh. Now at 30 minutes in, she's showing 4 images that look the same in the amplitude domain. Okay, and this shows the extent to which this measurement relies on information in the phase domain. Okay, so she explains that an image with a hole or without a hole looks the same in the amplitude domain. So you have to have phase data. But then, at 39 minutes in, she says that the phase data is completely unusable and the amplitude data is noisy. So she used unusable data to get her images of black holes? It's like she contradicts herself 3 different times in this talk. A clever commenter who read this material when I first wrote about it on Quora wrote, "Take a look at this picture of my cat." And then he sent a picture of static. You don't see a cat, you just need to apply the right cat-shaped filters. The lesson is, if you have noise, you can design an algorithm that can filter out whatever you want to see in it. And when I see this happening on the front page of newspapers across the world, I have to conclude that our academic system has succumbed to just overwhelming noise. I should mention some pre-existing biases because my default setting is skeptical, and I don't really believe that black holes exist because I think that theorists got drunk on general relativity and invented them. And I think that astronomers got drunk on interpreting the meanings of tiny dots of light, and they convinced themselves that they had seen these invisible theoretical beasts of the night sky. So seriously, anytime you use a singularity to describe a physical phenomenon, it usually turns out to be wrong. Just think about the equations governing water swirling around in a basin. If you use one type of equation, you get a singularity in your basin, and if you use another type of equation, you don't. This is one reason why I think that using general relativity to extrapolate about things you can't even see, it doesn't make a lot of sense. I mean, general relativity doesn't even work to describe galaxies. They have to invent invisible matter to make it match what we see in the sky. That means the theory isn't very good. So why should we use the theory to create black holes? The idea that the whole universe is full of singularities floating around in space just requires a suspension of disbelief with which I'm not really comfortable. And I'm not alone in this. There are scientists out there who do not believe that black holes exist. 20 years ago, there were a lot more of them, but today, somehow, fashion has taken over and black holes are believed by everybody and put on the front page of newspapers. It's really weird. So some black hole researchers will display a picture of a star with a dark spot in it and then follow that up with a simulation showing the same picture. And non-scientists can be convinced by this sort of argumentation. But if you've ever actually done simulation work, there's something that you know that other people might not know. If you have a picture of something, it is really easy to make a simulation that copies the picture. What is hard to do is to make a simulation of something you've never seen before, predict how and where you will see it, and then record an observation of it. That is really the only way to do science, because any other route can lead to self-trickery. And that's what I think that this group of black hole researchers has done. And the fact that it ended up on the front page of newspapers across the world just tells me that something's really broken. There was some older research that claimed to support the existence of black holes that I read recently, but when I read it more closely, I saw that it was really just tracking some stars near the center of our galaxy. For example, they wrote, "The stars in the innermost region of our galaxy are in random orbits like a swarm of bees. However, further out, 6 of the 28 stars orbit the black hole in the center of our galaxy in a disk." 6 out of 28? In this respect, the new study has also confirmed explicitly earlier work in which this disk has been found, but only in a statistical sense. Ordered motion outside the central light month, randomly oriented orbits inside. That's how the dynamics of the young stars in the galactic center are best described. Okay. I believe their measurements, but I don't always believe the interpretation which scientists give to their results. So when I see this, I think you have 6 out of 28 stars doing what you think they would do if there were a black hole there, but the rest don't. And they only do what you think they should do in a statistical sense. This tells me that there is no black hole there. You've basically excluded that, yet you've interpreted your data in the opposite way. This level of delusion is really bizarre to see. A lot of money goes into making these sorts of simulations and studying black holes. So maybe I'm naive to expect less resistance to a change in belief. Although I have a video in my post from Veritasium, and he's somebody people trust, and he doesn't come out and directly question the existence of black holes. But he does give a little bit of flavor to the idea that astronomers pick unlikely scenarios out of thin air and then use them to explain the qualities of blurry blobs of light. I find it amazing how artists' renditions and just so stories pass as science in this day and age. Science should produce progress, but when it swirls around in an eddy of self-citation, you end up with a black hole in a figurative, not literal sense. Thank you for watching. I hope this gave you some food for thought, and please tune in for my next videos. Until then.